Good morning, students. Welcome back for our second lecture this week for our first part of our Chem 212 review. When we finished last time, we had just finished talking about acids and bases, and we had discussed the two definitions of acids and how to use arrows to indicate acid-base reactions and also evaluate the strengths of acids and bases. Remember the Bronsted-Lowry definition of acid being a molecule that donates a proton or H plus ion. A base is one that accepts one. And a Lewis acid, similarly, is one that shares a pair of electrons to make a bond. And the reason why this works is because generally in an acid-base reaction, it's going to be the hydroxide that is donating a proton, or a pair of electrons to the H plus. And so this has a negative form of charge here. And so even in this definition encompasses the standard definition of accepting a proton, the acid accepting a bond here, the acid here being the boron trifluoride, the acid accepting the pair of electrons, and the base here being the water donating the pair of electrons, which is analogous to the hydroxide here being the base donating the pair of electrons. So this is an even more broad definition of acids and bases that can encompass reactions that do not necessarily involve protons or hydroxide ions, but also includes that definition as well, the standard Bronsted-Lowry definition. Now, when it comes to hydrocarbons or alkanes, often perspective is very important. We're looking at these molecules in 3 dimensions, and we care about where the atoms are positioned in 3 dimensions. So we have various ways of viewing these molecules. One is just the standard line drawings that we've been used to seeing, the bond line angle drawings, but there are others as well that are useful in different situations. For example, the Newman projection is very useful when you're trying to make sure that certain atoms are in certain positions relative to one another, or the molecule needs to be rotated in order to get the atoms in that position. This is especially useful in elimination E2 reactions, in which you must have a hydrogen atom and a leaving group in the same plane for the reaction to occur. The way that a Newman projection is drawn is that if you're looking at a molecule like this one from left to right here, those atoms here that are on a wedge, so this would be like a wedge here, with this is called a sawhorse projection, and then this would be a dash going back into the page, and here this would be a wedge, and this would be a dash. That's the other way of exhibiting these. And when you're looking left to right, the wedges are on your right, so they'll appear on the right side of a Newman projection, where this part here with the point represents the front carbon, we're here with these red hydrogens, and the circle in the back represents the back carbon, and we're looking down any bond here that has 2 carbons. Now, if you happen to look in the other direction, from right to left, so if you're told to look this way, then the wedges will be on the left of your Newman projection and the dashes will be on your right. Either way, the relative positions of the atoms are preserved, and this Newman projection allows you to see these very closely. For example, if we look at these 2 hydrogens, the one going the one in the front here is in the same plane as the one in the back, and so here we can recognize that these hydrogens are in the same plane. Now, sometimes we have more complex molecules, ring molecules. In particular, we're often very concerned with cyclohexane and cyclopentane, but cyclohexane in particular because many organic molecules and biological molecules, as we will see, contain cyclohexane rings as a part of their structure. So hexane here, we're going to talk about naming a little bit later, but hexane meaning that there are 6 carbons in the longest chain here, which goes all the way around in a ring, and so that's why we precede it with cyclo. In this ring, the reason why this ring appears so often in nature is because it has no angle strain, meaning all the angles here for these carbons have tetrahedral geometries, and thus their bond angles are 109.5. And by adopting this so-called chair configuration, cyclohexanes can have 109.5 bond angles everywhere, resulting in no angle strain. Also, if we look at this with a Newman projection, we will see that all the hydrogens are in what we call a staggered formation, whereas the alternative here would be an eclipse formation, which is a high energy formation because the hydrogens are in the same plane here, and we have some interaction between the electrons in their bond that repels them. But when they're in this staggered configuration, where these have a dihedral angle of 60 degrees, this allows for no torsional strain, and so this chair structure becomes a very a very low energy structure relative to other potential cyclohexane conformers or ways of arranging this. Of course, all these bonds are single bonds that can rotate. There are other possible conformers or shapes that this can adopt, such as the so-called boat shape, where this part is tipped up. But this is the lowest energy shape. And it's often useful to build this in a model so you can see what's going on here. What you'll notice is that some of these hydrogens here are pointing straight up and some are pointing straight down here. We call this the axial position. And when we have large groups together in the axial position, they tend to have some crowding of each other, which we're going to refer to as steric strain. So it's important that you have a facile ability to draw a cyclohexane ring to show these arrangements here. This is done by drawing two parallel lines, as so. With on one end we have a slightly lower end, on the other end we have a slightly higher end. Then you draw two parallel lines here that slightly cross over in the middle but are parallel, and then we draw two parallel lines to complete the cyclohexane ring. So just to show you how that would be done, we go like that. So notice that this top is slightly higher than this one. Then we draw two parallel lines this way that slightly cross each other, a little bit higher like that. And then finally we complete it with we make these long enough so that when we complete it, these are two parallel lines, this one and this one right here, and that completes our ring. And then we have these so-called axial positions, which are shown here. So if any substituents are attached on the lower end or the foot of the cyclohexane, we'll have a axial position straight down on the ring if there's anything bonded here, such as a hydrogen atom or other groups. And at the head of this, we'll have another axial position. And then the axial positions go up, down, all the way around the ring. So this is the down position, then up, then down, then up, then down, then up. And these are, and you notice I've crossed over my line because I made them so short. In this picture it didn't. Either way is fine here. And then alternatively, we're going to have equatorial positions as well, as you saw. So let's take a closer look at that. Whoops, I drew over this, but 6 of these are axial. The remaining are going to be equatorial. Now, the way you know how to draw these is that if you look at a flat projection of the ring, some substituents, their orientation can be indicated with a wedge, meaning they're popping out of the page. I'm going to call this up. I'm going to call the wedges up, and I'm going to write them in the straight up position on the ring. And then the dashes, I'm going to call these down. And so here the chlorine is up and the methyl is down. So if I make, and I can make any carbon atom the head or the foot of my ring. In this example, I've happened to write the chlorine atom as being the head of the ring. And so since it is up, I draw its position straight up. And that is an axial position at the head of the ring. And the methyl position here is down. So remember, axial goes up, down. So this methyl position will be down. And we can see that they are both axial in this case. They're both axial. Now, we can draw this another way in which we flip the ring. So you can flip the ring, and when you flip the ring, what is occurring is that the head, the foot is becoming the head, and the head is becoming the foot. And all of the axial positions turn to equatorial, but they still stay up and down. So given that this is the foot of the ring, I'm going to draw in the axial position. So the axial positions go up at the head of the ring and down at the foot of the ring. And then they go up, down, all the way around. So this is up, down, up. And so this hydrogen is in the axial position now. So you can see this red hydrogen change from being an equatorial position to an axial one. This hydrogen here also switched from being an equatorial position to an axial one. However, the hydrogen here, the red hydrogen, is still in the up position. It's up, and that does not change. This is up equatorial on the left here. This is up axial on the right. Still up, though, but went from equatorial to axial. And here this blue hydrogen was down equatorial, and now it's still down, but it's axial. And likewise, the chlorine went from being up and axial to now it's up and equatorial. And the methyl went from being down and axial, now it's down and equatorial. And I'm going to show you how you properly draw in those equatorial positions as well. This is how you do it. You're going to notice something. This hydrogen here, its equatorial position is parallel to this line right here. And this hydrogen here, its equatorial position is parallel to this line right here. The equatorial position right here, equatorial, if we had something there, is parallel to this line right here. So the equatorial positions are always parallel, drawn parallel to the line opposite them. And so we can complete all the equatorial positions. I completed all of them on all the equatorial positions, all the axial positions rather, on the last slide. If I complete all the equatorial positions, this one's equatorial, it is parallel to this one. This one will be equatorial, and it's parallel again to the opposite one, which is right here or right here. So this will be equatorial like that. For this one here, these are also again parallel to the line that they are opposite from. In this case, it's this line or this one. So the equatorial position is like this. And for this one, it is also here parallel to these lines here, one space away. And so it will also go like that. And that will complete all of our axial and equatorial positions there. So it's important that you're able to draw these so that you can analyze which are in axial positions, which are in equatorial positions. In terms of stability, the molecule becomes less stable when you have large groups that are both on axial positions on the same side. So for example, if I have a large group here in the axial up position, or here in the axial up position, there will be what's called steric hindrance due to the crowding of these, which are all pointing upwards, and so all are parallel to one another and crowd each other's positions. However, in the axial position, they spread out outwards away from the ring, and so they don't have that steric hindrance. So you're going to have your least stable cyclohexane is when you have large groups that have these 1,3 diaxial interactions where they're one carbon away in both axial. Now, so those were the main points of chapter 4. In chapter 5, what we were focused on was the three-dimensional arrangements of atoms. So we started to get into that with the cyclohexane, and so chapter 4 was all about various ways of writing down and showing various alkanes or molecules with carbon-carbon single bonds only. What we have not discussed, or we maybe just started to discuss, was the three-dimensional arrangements of these atoms. So when you have two molecules that contain the same atoms but they are arranged in a different way, we call those isomers. And isomers come in two large categories. One is constitutional isomers, in which the atoms are bonded in a different way. An example of that would be like methanol, which contains 2 carbons, 6 hydrogens, and 1 oxygen, as opposed to methoxymethane, or dimethyl ether as it's often called, which also contains 6 hydrogen atoms, 2 carbon atoms, and 1 oxygen atoms, but they are bonded in a different way. The other type of isomers are stereoisomers. And in stereoisomers, all the atoms are bonded to the same other atoms, which is different than here, right? Because here both carbon atoms are bonded to the oxygen. But in this left example, only one carbon is bonded to the oxygen. So these are constitutional isomers. In stereoisomers, all of the molecules are bonded to the same other atoms. They're just bonded in a different way. Now, when it comes to rings and carbon-carbon double bonds, because there's a ring or carbon-carbon double bond, the single bonds are unable to rotate. So this leads to the potential for stereoisomers. And one type of stereoisomer is what's called the cis-trans stereoisomer. And this is a kind of vague terminology. This terminology does help us, though, to some extent. It helps us to very simply state whether groups are on the same side or on opposite sides. It's possible to be more precise with this, and we're going to have some other terminology that is a bit more precise. However, we'll come to that a little bit later. But with this ring, because the single bonds cannot rotate, you can have a situation where, for example, you have two methyl groups that are on the same side, or you have methyl groups that are on opposite sides. When they're on the same side, we call that cis. When they are opposite sides, we call that trans. And so here is a cis isomer on the left, and on the right is a trans isomer. So this can also be indicated with double bonds. So here, for example, this is considered trans because the two hydrogen atoms, which are the same, are on opposite sides of the double bond, whereas in this example, these fluorines and these hydrogens, there are two hydrogens here too, just not shown, but this would be considered cis because the two fluorines are on the same side of the double bond. And this one here, this is considered trans because the two identical groups are these ethyl groups, ethyl meaning two carbons, YL meaning branch. These are on the same side or on the opposite sides rather, so this is called trans. Now you might be wondering, what if there are 4 different groups attached? And that is actually a situation that definitely does occur, right? And you have to be careful about it. You have to watch out for it. And there's going to be more precise terminology that we can use for that. I'm just going to turn off my camera. I am having okay. Now for the other type of stereoisomer is called an enantiomer. And enantiomer arises due to a property called chirality. And chirality generally occurs chirality is a mathematical property that describes many things. But it refers to a non-superimposable mirror image. So these two molecules here, they are mirror images of one another. However, they are not the same molecule. If you build two models like this and try to take one and turn it and put it on top of the other, you're going to see that that cannot be done because they are actually distinct shapes. In the same way that you cannot take your two hands and superimpose or put them on top of each other because one is left-handed and one is right-handed. So these mirror image molecules that are not superimposable, these are referred to as enantiomers. And these enantiomers, you can spot them because they will contain at least one chiral center, and that meaning a carbon that is attached to 4 different groups. In this case, a methyl group, an ethyl group, a hydrogen group, and a hydroxyl group here. So when we want to indicate here the difference between one enantiomer and another enantiomer, so the word I'm using here is enantiomer. It's not on the slide, but you've heard it before. Enantiomer or optical isomer, they're also called. You've heard of it in Chem 212. These are enantiomers of one another. When we have enantiomers, we want to be able to distinguish between one enantiomer and the other enantiomer. And the way we do that is with this so-called Kohn-Ingold pre-log system. We take the 4 groups that are attached to the carbon and prioritize them according to their atomic number. And then we arrange the molecule in space so that the lowest priority group is on the dash or facing away. Then we count the priorities of group 1, 2, 3, either in a clockwise direction or a counterclockwise direction. If the groups with priority 1, 2, and 3 are positioned around in a clockwise direction, we call that R. And I remember R as right-hand turn. So when you turn a steering wheel clockwise, that's a right-hand turn. So that's why I remember clockwise is R. And then counterclockwise is S. That's a left-hand turn. S stands for sinister, which is Latin for left-handed. So in order to designate these configurations, again, here we have a chiral carbon. So we first recognize the chiral carbon. We can see that it's a chiral carbon because it is attached to 4 different groups here. 1 chlorine, 1 hydrogen, 1 group containing 2 carbons here, and 1 containing an oxygen. And so when we look at this, we can see that the the number 1 group here is the chlorine that has the highest atomic number. The number 4 group, the lowest priority, is hydrogen, which has only an atomic number of 1. And then oxygen has a higher atomic number at 8 than carbon at 6. And so it has a designation of 2, and the carbon has a designation of 3. And at this point, though, however, we would have to determine the R and the S, we would have to rotate this molecule in order to put the 4th group in the back position and the number 1 group in the front position. And so a strategy for doing that is what I call the double switch. And so what you do is you draw out just a basic representation of the chiral carbon, and then you switch so that the priority 4 position gets on the back. So we're going to have the priority 4 position here now on the dash, and the priority 1 position on the wedge. But when you do that, when you do a switch like this, you're changing R to S or S to R. So to revert that and maintain your RS configuration, you switch the other 2 items as well. So the 2 goes here and the 3 goes here, and that doing a double switch like this, it is a shortcut to doing a rotation of the molecule, which is more difficult to imagine in your mind. But this essentially rotates the molecule, turning it around so that it ends up with the dash facing backwards. And at that point, now we have preserved the configuration by doing the double switch, so we can indicate the configuration. This is going 1 and then 2 and then 3. That is a left-hand turn, so this is an S configuration. Here's another example here. In this one, the hydrogen is not drawn, so we can draw it in. Now the hydrogen's already on the dash, and it's going to be group priority 4, and so that makes things very easy for us. We don't have to do a switch like this. This will be 4, this will be 1. And then what I'm going to show you on the next page is that sometimes when we have a tie, what we do is we break the tie based on what's attached to this. So here carbon is attached with, here, this is carbon, there's carbon right here, carbon right here, and carbon right here. So those are the same atomic mass. However, what we can do is look at what they're attached to and compare that. So this carbon, accepting the carbon that we came from. So we came from this when we're looking at this carbon. This carbon is attached to 3 hydrogens. So we can write those down as hydrogen, hydrogen, hydrogen. This carbon here is attached to 1 more carbon. So this carbon is attached to 1 more carbon and 2 hydrogens. It's right here. So it's attached to carbon, hydrogen, hydrogen. Since the carbon has a higher mass, atomic number rather than the hydrogen, it gets the higher priority. So we call this priority number 2. This one's number 3. And so here we have on the chlorine is number 1, and then number 2 is this way, and number 3 is this way. This is a right-hand turn, so this designation R. And as I showed you on the last example here, this is a slide to show what I did, but by doing a double switch, that simulates a rotation. So this is the same molecule from last time. When we do the double switch, it simulates the rotation without us having to keep track of everything in our heads, which is really hard. And it preserves the RS because it doesn't change the position of anything. It just rotates the molecule along this axis. And you just switch here. Make sure that the 4, however, you can double switch any of them. as long as you make sure that the 4 ends up on the dash. And that's what we did on the last slide. As I mentioned in the other example, sometimes you'll have a tie when you're trying to make a designation here. So this is our chiral carbon attached to 4 different groups: hydrogen here, hydroxyl here, and then this whole chain is different from this one here. And what we have here is for this one, oxygen gets group priority number 1, hydrogen with the lowest atomic number priority number 4, but then we have a tie here. And unfortunately, unlike the last time, this carbon is attached to one other carbon and then 2 hydrogens attached to it. The 2 hydrogens are here and here. And then this one has 2 hydrogens here and here too. So it has a carbon attached. Whoops. It has a carbon attached here and then 2 hydrogens. So it's still tied. And so when it continues to be tied like this, we go down as to the next here, the next carbon, and we're going to assign, we're going to look at what that is attached to. So this carbon here, we're not going to look back. We don't look back when we do this. We only look forward. So this carbon has 1 hydrogen attached, and it has 2 carbons, 1, 2, and a hydrogen. So we write CCH. Now this carbon here has 2 hydrogens attached, and then again, we don't look back. We don't look back here. We only look forward. So if we're moving forward along the chain, we have 1 carbon and 2 hydrogens. And so since this second carbon attached to this one beats the hydrogen, which is the second group here, this leftward direction here gets the priority number 2, and the rightward one gets priority number 3. However, in this case, so we have this is group number 4 here, this is group number 1. Unfortunately, we do not have group number 4 on the dash position. So we have to do a double switch. Again, we'll switch 1 and 4, we'll switch 2 and 3, and we'll write a new representation of this. And so wedge, dash, line, line. The 1 now will go on the dash, the 4 will, or on the wedge, 4 will go on the dash, then the 2 and the 3 switch positions. So the 3 will be on the left, the 4 will be on the right. The 3 will be on the left, the 2 will be on the right. And then our arrangement is 1 on the top here, 2 over here, 3 over here. And so this is a clockwise right-hand turn. This is R. 1, 2, 3. Right-hand turn. Turn the steering wheel right. So that is an R designation. Note that the priority is not based on the sum here. So, for example, in this example, we have a tie here with this carbon and this carbon. But when we looked at what they're attached to, this left carbon is attached to an oxygen and then 2 hydrogens. So the sum of these atomic masses would be 10, right? However, that's not what matters here. What matters is that the oxygen is higher priority. Because on the right side, we have 3 carbon atoms attached. 1, 2, 3. 3 carbons. If you added these up, these would be 18. But that doesn't matter. What matters is that the oxygen is highest priority connected to this carbon. The carbon is the highest priority connected to this carbon. And so oxygen beats carbon. So this left side gets designation 2. This right side gets designated 3. And again, we'd have to do a double switch here. This is priority number 4. This is 1. And so if we did the double switch, the wedge would get the 1, the dash would get the 4, and then we'll switch to 3 and 2. Here we have 1 and 2 and 3, and so that's a right-hand turn. Let me double check. I did that right, that one too. Same as the last one. And so that's how you do the tiebreakers for assigning the R's. And that's how you assign R and S to a chiral carbon. So we've been discussing so far enantiomers, which are non-superimposable mirror images. We have not discussed much about diastereomers. We did talk about cis and trans. So these are a kind of diastereomer. They're a diastereomer because they're not a mirror image. Okay, this molecule on the left is not a mirror image of this one on the right. But the atoms are arranged in a different arrangement in 3-dimensional space. They're not constitutional isomers because all the atoms are connected in the same way. Carbon, 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 carbon. The difference is that in 3-dimensional space, they're arranged in a different way. So cis-trans isomers are a type of diastereomer, but they are a type of stereoisomers. So let's talk a little bit more about diastereomers. Diastereomers, the number of diastereomers will depend on how many chiral centers you have. And so in total here, for every chiral carbon you have, you'll have 2 enantiomers. And so this molecule is the enantiomer of this one. And you may be wondering, how can I know that? Well, the easy way to take one molecule and make its enantiomer is to just take all of the wedges and change them to dashes. And that will make the mirror image of the molecule for you. And so this molecule on the right is the enantiomer of the one on the left. Same here. So this molecule here, if we go from this molecule over to this one here, all the dash here has been changed to a wedge. Both these wedges have been changed to dashes. So these are enantiomers. For the same reason, these are enantiomers and these are enantiomers. But all of these are diastereomers of one another. These four pairs here are diastereomers of one another because they have all the atoms arranged in the same way, but they're arranged differently in 3-dimensional space. Now, these two are enantiomers because they're mirror images, but these, let's say this one here and this one here, they're diastereomers because although they are stereoisomers, they're not mirror images of one another. This has a dash in the position where this has a wedge. These are mirror images, these two, but this one and this one are not mirror images, or this one are not mirror images, but they are all containing the same atoms bonded to the same other atoms, just arranged in 3-dimensional space. So these are 4 pairs of diastereomers. Your total number of diastereomers and enantiomers will be 2 to the power of the number of chiral centers. So this has 3 chiral centers. So the number of diastereomers and enantiomers, the total number of stereoisomers is 2 to the 3rd power, which is 8. If you have 2 chiral centers, it would be 2 squared, which is 4. If you have 1 chiral center, you only have a pair of enantiomers, if that. So you'd have 2 stereoisomers. Now, there is an exception to this, and that is that if you have a molecule that has an even number of chirality centers, and it is arranged such that there is a plane of symmetry within the molecule, you will have what's known as a meso compound. And that meso compound does not have an enantiomer. An example here is this dimethyl cyclohexane, and we can redraw this too in another way. We could draw it like this too, and this would give us the same type of this is drawn in 2 dimensions rather, and as flat from the top view, and we can still see that this has a plane of symmetry in the molecule because both these wedges are on the same side. So this is called a meso compound. A meso compound does not have an enantiomer due to its symmetry, and it can either have a plane of symmetry or it can have a kind of rotational symmetry to it. This one also has a rotational symmetry. The reason the rotational symmetry is such that if we had the same molecule, so let's say we want to try to draw the enantiomer. We try to draw the enantiomer here. So we change all the wedges to dashes. Well, that's not going to work because if we take this molecule and we flip it like a pancake, then both of the dashes will become wedges and it will look just like the one below. So this changing the wedges to dashes here does not make a new enantiomer because this is a meso compound. So these are not 2 enantiomers, these two. These are the exact same molecule. They are not enantiomers. Now, notice, contrast this with a molecule like this one here, which is very similar, but it does not have a plane of symmetry. If we have this and this, now this has an enantiomer. If I change the wedge to a dash and a dash to a wedge, when you flip this one like a pancake, so these are enantiomers. When you flip this like a pancake, it does not produce the same molecule. If I flip this, imagine taking this and flipping it in your mind. If you flip it sideways, so I'm talking sideways like we're flipping it in this direction, sideways like a pancake, this dash will now be a wedge. It will not be a dash like this one. It will be a wedge because it will now be popping out at us. And this wedge will go over here and it will be a dash, not a wedge. And so when you flip these, you do not get the same molecule. They're not enantiomers because they do not have a plane of symmetry like this one. So that's very important to watch out for. And sometimes you don't have an enantiomer when you have a mesocomp. Besides the Newman projections and these Haworth projections like that and these flat top-down projections, there are also Fischer projections. Fischer projections are going to become significantly more useful later on when we talk about carbohydrates in this class. What you need to know about Fischer projection is they are drawn like this, where we do not seem to indicate any chirality. However, what is represented when we draw these straight lines like this is that those atoms that are on either side can be indicated by wedges, and the ones that are vertical can be indicated by dashes. And at that point, you can rearrange this a little bit and rotate it, and end up, for example, putting these two on a line, and then this one would still be a wedge, and this would still be a dash. We're going to get a little bit more into this when we talk about carbohydrates, but you should be aware of what these Fischer projections are trying to represent. Finally, for alkenes, alkenes also have stereoisomers. Alkenes meaning molecules with carbon-carbon double bonds. And in the past, we use cis or trans earlier in this lecture to indicate the relative positions of groups on the bond. We said if they're on the carbon-carbon double bond, if there are two groups on opposite sides of the double bond, we call that trans. And if there are two groups on the same side, we call that cis. However, that only works if you have two of the same groups on either carbon. What about this molecule here? It does not have two of the same groups on either carbon. Every group on the two carbon-carbon double bond carbons are different. And so we need a more precise way of indicating the stereoisomerism and the difference between two diastereomers. And we're going to use this so-called E and Z designations for this. So if we took, what we do is we look at each carbon in the double bond, and for each group attached, we assign the group a priority the same way we did for R and S, based on atomic number, and in the same tie-breaking fashion as well. So here, the fluorine has a higher atomic number than carbon, and so the fluorine is the priority 1 group on the left side, and the carbon here, the ethyl group, is the priority 2 group. Then we assign priorities on the right side. Nitrogen has a higher atomic number than hydrogen, so it gets the priority 1 group, and the H gets the priority 2 group. And then we look and see, are the priority 1 groups on the same side or not? Here they are on the same side. So when they're on the same side, we say they're on the same side. Z, on, Z, same side. Okay, they're on the same side. They're Z. So here we have both of these are on the same side. They're Z. E is the opposite. It's opposite sides. So if the two groups are on opposite sides, then we would indicate it that way. This one, it happens to be Z. And then the other situation, if this nitrogen and hydrogen switch places, for example, now the fluorine and the nitrogen are opposite sides, so we would call that E. And so that's how you designate between E and Z. And what's very important is that when you are writing the names of molecules, you must watch out for a situation in which you have chiral carbons, because then you will have to also designate R or S to complete the name. And you're going to watch out for situations in which you have double bonds, because you may have to indicate E or Z if there are two different stereoisomers. And so this is a big wall of text. I'm not going to read it to you. These are the complete or relatively complete rules for how to assign names to molecules. We find the parent hydrocarbon, which contains the highest priority functional group. I will list the priorities of the functional groups on the next slide. And the parent hydrocarbon is going to be the longest continuous carbon chain that contains the highest priority functional group. If there are two chains of equivalent length, you'll choose the one with more branch points as the parent. You name the parent chain using a numerical prefix that indicates the number of carbon atoms and a suffix that is consistent with the highest priority functional group. Then we'll assign locants in the parent chain. We begin at the near end near the first branch or the high priority group. I think that's important to mention. It's not specifically mentioned. uh, or the highest priority group, if there is a high priority group. Because the highest priority group is the most important, that should always have the lowest number. Then we're going to identify the substituents. We will name those. We write down the names of single word substituents, are written in alphabetical order, ditri, and their names of the substituents often, they depend, but they often end with YL if they're a branch. And there are other substituents such as chloro, bromo, so forth. That's the way we handle halogen substituents. We also have like other substituents with oxygen that are low priority. This would be called methoxy. Meth meaning one carbon, oxy meaning there's an oxygen on the substituent. There's also ethoxy, propoxy, and so forth. If there's sub-branching, we may have to apply a special name for certain sub-complex branches or name the branch separately and end it with a YL. So our parent chain numerical prefixes for 1 carbon are meth, 2 carbon are eth, so forth, all the way down. There are more of these, but I only expect you to know up to number 12 of them. And then we end the parent chain with a suffix name that depends on the particular group. Now or the particular functional group. Now, in our previous class, we only did alcohol, alkene, alkyne, alkane, ether, and alkyl halide. In this class, we're going to start to name amines, ketones, aldehydes, nitriles, amides, esters, carboxylic acids. Currently, our highest priority group is the alcohol, followed by alkene, alkyne, and so forth. And we write the name such that the end of the name is consistent with the highest priority group. If we have a lower priority group, or if we have, for example, a lower priority group along with on the same molecule as the higher priority group, we use the prefix name here and we name it as a substituent and consider it alphabetically. So here we have two examples. One is an alcohol, and one thing I want you to notice about this alcohol is that there is a chiral carbon. This carbon here is attached to 4 different groups, and so we're also going to have to do R and S. Now also our highest priority group is the alcohol, so that's going to contain our parent chain. It must contain that group. So we can number the substituents, and because our alcohol is closer to the left, we're going to number left to right, starting on the end closest to our highest priority group. And we can either call this carbon at the top 5 or this carbon on the side. I'm going to call the one on the side carbon number 5 just because I think it looks a little nicer. And so now we can see that we have the parent chain here containing 5 carbons, so this will be the parent chain here. And then we're going to have a branch here. This branch contains 1 carbon. And so for branches like this, alkyl branches, their names end with IL. So you can see here, alkyl, their names end with YL. And so this is going to be ending with YL. And since it contains 1 carbon, the prefix will be. So this is methyl. And so now we also need to get a designation for the priorities here, which I'm going to use green for. The oxygen will be priority 1, the hydrogen will be priority 4, and then here this is going to have HHH attached. It's a carbon with HHH attached, and this carbon has a carbon and 2 hydrogens attached, these ones right here. So it's carbon, hydrogen, hydrogen. The carbon beats the hydrogen, and so we're going to call this group priority number 2, and we're going to call this priority number 3. And so if we see this, it goes 1 and 2 and 3. It's a right-hand turn, so this is going to be R. So now we're ready to write the complete name, and usually you'll see that I write the name kind of back to front. Now this contains 5 carbons, so the prefix is going to be pent for the parent chain. It's got no double bonds, so that's going to be followed with an instead of ene. Ene would be if it was a double bond. And then it's going to end with all, because it's an alcohol, the highest priority group. The alcohol is positioned on the 2nd carbon, so we're going to say 2, and we separate the letters and numbers always with dashes. We say 2-pentanol. That's the name of the parent chain. Then we've got one substituent here, which is methyl. So that methyl is on the fourth carbon, so we're going to say 4-methyl 2-pentanol. And finally, we have a chiral carbon here on the second carbon. So we're going to say R 4-methyl 2-pentanol. Now, we can also say 2R. If you have more than one of these, you'll have to write them separately and separate them by a comma. But you can either write R here or 2R because that's the only chiral carbon. Okay. Next, we have this one, this example on the right. Now, in this example on the right, notice that we have a double bond. And this double bond has 4 different groups attached. So we're going to have to be careful to use the E and the Z here. Now, chloro, the halos, they're not a priority group here. So our parent chain here has to contain the double bond because it's the highest priority group. And so this can be our parent chain here. And we're going to number this such that we start on the side closest to the double bond. So this would be carbon number 1, carbon number 2, number 3, 4, 5, 6, and 7. So since we have 7 carbons, our name here is going to be hept for 7 carbons, and ene is the suffix for a double bond. And this is going to be, since the double bond starts on the second carbon, this is going to be 2-heptene. And then this substituent here is a halo substituent, and so we end it with a O, so this is going to be called chloro. It's on the second carbon as well. And then we have to decide on E or Z. So in terms of priorities on each side, the chlorine gets priority 1 over the carbon, priority 2. This hydrogen here gets priority 2 because this carbon trumps it in priority. The priority groups are on opposite sides, the number 1 priority groups. So this isn't not going to be Z on the same side. It's going to be E, not on the same side. Okay, and so now we can write the name. The name is going to end with 2-heptene. Before that, we have a chloro group, so we're going to say 2-chloro. Remember, the numbers and the letters never touch, always separated by a dash. Finally, we have to indicate the E or the Z, so we're going to say E. We can say 2E or we can just say E because there's only one double bond. So if you want to write a 2 here, that's okay too. The double bond's happening on the second carbon. E2-chloro 2-heptene. And that's how you do nomenclature. We'll do more nomenclature as we move forward, so you'll have more chances to practice. At this point, my lecture, I'm just going to continue. We have a little bit left here. Yeah. I'll just finish up this. Well, yeah, it's going to be a kind of long one, but let's finish this up. So, in chapter 6, there's various. Chapter 6 is all about energy in reactions, and so explaining why reactions occur. So we look at 2 different types of energies. One is called enthalpy, or the heat energy, that is often comes out of a reaction. You see many chemical reactions involve the loss of heat. This is an example of figure 6.1 here, showing that when 2 atoms that have their own atomic orbitals bond with one another, they produce new molecular orbitals with their atomic orbitals. And one orbital is lower in energy, the other is higher. And so when the bond is formed, energy is released. And that's generally true. So when a bond is formed, energy or enthalpy is released. When bonds are broken, you have to put energy in. And so we can kind of predict the enthalpy either numerically or just based on our understanding of relative bond strengths. And so this is a great skill that when you become a very good chemist, you have a kind of sense of the approximate strengths of bonds. And I'm going to give you a little bit of a sense of that now. What you're going to see is that bonds to hydrogen tend to be very large in energy. And this is because hydrogen is a very small atom, and so it tends to make very short bonds. This usually, often, The shorter the bond, the stronger, although not always. There are other competing factors, which I'll talk about. But you can see this in the pattern with the haloalkanes here. Fluorine is smaller than chlorine, which is smaller than bromine, which is smaller than iodine. And so here, the size of the length of the bond is what's dominating because they're all bonded to hydrogen. So as the bond gets longer and longer, it gets easier to break. And I like to think of that as like a piece of wood. If it's a long piece of wood, you can karate chop it very easy. But if it's a short one, it's hard to karate chop, right? And so the HF is the hard to karate chop short bond. The HI is the easier to karate chop long bond. And so it's stronger. You can see a HO bond being about slightly, the HO bond is slightly longer than the HF bond, so you can see that the bond energy is slightly less. Now, when you have carbon-carbon bonds, you have a similar situation. So these are all carbon bonded to other things. Again, when you bond to a larger atom, you get weaker bonds. Now, there is an exception to this with very, very electronegative atoms, such as oxygen and fluorine and chlorine. When you have two very electronegative atoms bonded to one another, even if it's a short bond, it ends up being weak because both atoms are pulling on the electrons so hard that they're essentially pulling their own bond apart. And you can see this very well with fluorine bonded to fluorine. The fluorine pulls on these electrons so hard, it essentially pulls the bond apart, and it breaks so easily. Chlorine has this to a lesser extent. Another bond that does this to a great extent is oxygen. Oxygen-oxygen bonds are also extremely weak. As we've seen, they're called peroxides. This is called a peroxide bond. And it's for the same reason as the fluorine-fluorine and chlorine-chlorine bond. It's because the oxygen is so electronegative that it's pulling its own bond apart, and that weakens the bond. And so these are the patterns in bond energy, and you can see that short bonds tend to be strong, longer bonds tend to be weak, but watch out for two electronegative atoms bonded together. So that can give you a really good sense of which bonds are stronger and which bonds are weaker. So when you want to look at a reaction, evaluate whether energy was released by the reaction or consumed, you can think of various situations. Like if you have a bond forming, okay, when we have a bond forming, well then energy is released when bonds are forming. If you're breaking a bond, you have to put in energy to pull those atoms apart because they're bonded. So this is energy released. So this is delta H is going to be a negative number. Here energy will be absorbed, so delta H will be a positive number. That's the number we say delta H is positive when energy absorbed. Now often you have more than one bond breaking and more than one bond being made in a reaction. So if you have to break a strong bond, that takes a lot of energy. And then if a weak bond is formed, you don't get very much back. And so that's going to cost you energy overall. So the delta H in a situation like this would be positive. You'd have to put energy in. If you only have to break a weak bond, but you're forming a strong bond, you're going to get energy out. So delta H will be negative in that case. So that's a way that you can predict what the delta H of a reaction without having exact bond energies to calculate it. And that's usually what we do. We don't usually calculate the delta H exactly like you would do in general chemistry. We just kind of estimate. We mainly want to know if it's positive or negative most of the time. Another factor that affects whether reactions go and how quickly they go is entropy. So most reactions are exothermic. However, there are endothermic reactions that occur. And they occur because they are dominated by entropy. And entropy can be thought of molecular disorder or randomness. It's more accurately thought of statistically in terms of the number of states that a molecule can be in and their energies can be distributed over. This happens as molecules become more free to move about. So, as I said, entropy can be thought of molecular disorder. So any situation where the molecule is free to move around a bit more and wiggle around a bit more, or the molecules are free to move in a larger space, or they're moving more quickly and more randomly due to a higher temperature, that will be a higher entropy situation. So a ring structure, for example, has less entropy than a branch structure, assuming the exact same atoms. Again, the more atoms you have in the molecule, too, the more positions and states it has. So bigger molecules can have more states to them. And if you have gases contained in a smaller area, when you get more gases or more spread out gases, you also have more entropy. Finally, we can determine whether a reaction will be spontaneous or not based on the delta H and the delta S together to combine to form to determine a property called delta G, which is related, in fact, to the total entropy of the universe. So it's defined as minus T delta S total for the entire universe. And when T delta S is positive, we say that the reaction is spontaneous. So that would be when a reaction is negative. And spontaneous just means that it's going to produce more products than at equilibrium, or by the time the reaction is done, than it has reactants. So for this reaction here, if we wanted to evaluate if this reaction is spontaneous, we would want to evaluate both the delta H and the delta S. When we look at the delta H here, what we can see is that we are breaking 2 pi bonds. These 2 pi bonds are gone. We still have 1. And we are forming 2 sigma bonds. So we're losing 2 pi bonds, and we're gaining 2 sigma bonds. The sigma bonds being the bond right here, here. So in that, sigma bonds are due to direct overlap of orbitals and are generally stronger than individual pi bonds. And so here we are breaking weaker bonds and forming stronger bonds. And so that means we're going to get a net energy out. So our delta H will be negative. We're gaining energy by breaking weak bonds and forming strong bonds. Finally, in terms of entropy, we started with 2 molecules that had a lot of freedom of motion, but now we're down to 1. And so we're losing entropy here. And so our delta S is going to be negative. Now, if we want a spontaneous reaction, delta G will have to be positive. So we should think about which situations that would occur. Well, this entire term, since delta S is negative, this entire term will be positive. And how big the term is will depend on the temperature. So if the temperature is low, let's say the temperature is like close to 0, then this term will be very small, and our delta G will be negative due to the negative delta H. So this reaction will be spontaneous at low temperatures because the enthalpy term will dominate, making delta G negative. It will be not spontaneous at high temperatures. And that's because this positive term will become very large at high temperatures, and then that will dominate over the negative delta H term, and the delta G will be positive. And so this is a way that we can determine whether we expect a reaction to produce a lot of products and be spontaneous or not without actually doing any exact calculations, which is very useful in organic chemistry. So we say that if a reaction has a negative delta G, we call it exergonic. And in terms of energy, so we have an energy diagram here. You will have to evaluate and draw energy diagrams. Here we see that the reactants have more energy than the products. They have to go through what we call a transition state. We'll talk about that in a moment. But overall, energy is released, and thus the reaction is spontaneous. This is an exergonic reaction. That is as opposed to an endergonic reaction, one in which the delta G is positive. That means the reactants have less free energy, or G, than products. Here, reaction coordinate represents the progress of the reaction from reactants to products. So here, energy must be put in to cause the reaction to go. So the reaction will favor the reactants here. It will not be spontaneous. There will be more reactants when the reaction stops than there are products. So when the reaction seems to stop, that's what we call equilibrium. So equilibrium is where the rate of the production of products equals the rate of production of reactants. So as reactants are consumed in a exergonic reaction, this is representing an exergonic reaction, so we have free energy on the vertical axis, concentrations on the horizontal. As we produce products, the forward reaction begins to become slower and slower and less spontaneous, until we have a minimum value of G. When we have this particular ratio of reactants and products, at that point, the delta G for continuing the reaction will be positive. And so we would have to start to put energy in to produce more products than we already have. And when we reach this state, this is referred to as equilibrium. Equilibrium is the state with lowest free energy, and that's where this ratio of products to reactants is what you will have when the reaction appears to stop. So the reaction stops because as you consume reactants, so let's say we have reactants A and B producing reactants C and D, as we produce more and more reactants, the rate of the reaction, which depends on the concentration of the reactants, will become slower and slower, forward rate. And as we're producing more products, the backwards reaction will begin to start. So the C and D will also react to go backwards and produce A and B. And when that rate of forward and backward reaction is equal, we say that that is equilibrium. Now, the rate of a reaction, the rate of both the forward and the reverse reaction can be increased by increasing the temperature. So a higher temperature will make a reaction faster. The rate of a reaction will go faster if there's a greater concentration of reactant. So that's why as the reaction progresses, the forward reaction goes slower and slower. For a reaction to occur, molecules must collide with a sufficient amount of energy in order to break old bonds so that new ones can be formed. This energy is referred to as the activation energy and is represented here as a part of the rate constant. K is called the rate constant. So a larger activation energy will actually produce a smaller rate constant, which means a slower reaction. Geometry of the molecule matters. If a collision cannot occur because collision with an atom is blocked by many other atoms being in the way, that will slow a reaction down. And catalyst can be introduced, which is a molecule that is involved in the reaction but not used up in the reaction. That can make the reaction faster. When we look at organic reactions, we're often comparing the kinetics or the speed of the reaction versus the thermodynamics, the spontaneity of the reaction. So here, when we're looking at kinetics, what matters the most is the activation energy, which is represented by the difference in energy between the reactants, and this area here, this highest energy point in the reaction, which is referred to as the transition state. This is called the activation energy. As we can see, the activation energy for producing products C and D here is lower than for producing products E and F. So this reaction, this blue reaction, will occur more quickly than the red one. In addition, the delta G of the blue reaction is more negative than the red one. The delta G of the red one would only go from here to here. And so this reaction is also more spontaneous. So the blue reaction will occur and the red one will basically not. Products E and F will not be produced because products C and D are favored both kinetically with a lower activation energy and thermodynamically with a more negative delta G. Now that is not always the case. Sometimes some products will be favored kinetically but not thermodynamically. So what products you will get depends on how long you cook it. That's true in cooking as well. Sometimes you have to cook things low and slow, low temperature longer. Sometimes you have to cook things fast and at high temperature and you'll get different products and it will taste different, right? So here the red reaction is going to be thermodynamically favored. So E and F are kinetically favored. So this is E and F are going to be kinetically favored. So given a short time frame, products E and F will be produced rather than C and D. However, C and D now has a very high activation energy. So this is going to be a very, very slow reaction. But assuming that you can get it to go, eventually you'll get more and more C and D because the C and D has a larger delta G, a negative delta G. So this is thermodynamically favored. And a lot of times we're weighing the thermodynamics versus the kinetics to try to determine what amount of product will be produced in a certain amount of time. Here, assuming mild reaction conditions that aren't very high in temperature, we expect that products E and F will be produced preferentially to C and D due to kinetic favorability. But at high temperatures and long reaction rates, C and D will be produced more and more. Now, when we have a reaction, often it occurs through several steps. Each bump in an energy diagram represents one step in a reaction mechanism. So when I ask you to draw an energy diagram that represents a reaction, you should have one bump for every step in the reaction. The peaks here are high energy molecules that only exist for fractions of a second. These are referred to as transition states. The troughs here are referred to as intermediates. They are somewhat stable products, but they can easily be changed into other things, for example, returned back to the initial lower energy reactants, or ultimately used to produce this very low energy products. The transition state will generally, the transition state is basically the midpoint in the reaction. So here is the representation of a transition state where a chlorine atom is forming a bond with this carbon while simultaneously a bromine atom is breaking a bond. And we can see that this goes through this intermediate where this carbon is flat trigonal planar, and here this is very high energy, so this is going to immediately break apart and produce, will either go back and produce the reactants, or more likely it will produce the products. They are highly unstable and they cannot really be isolated or directly observed, because as soon as you try to interact with them, you turn them into something much lower in energy. So we can only speculate on the transition state. So sometimes I have you draw a transition state on an energy diagram showing this in-between state here. An intermediate occurs at an energy minimum. So these are not the lowest energy, but they're in between these very high energy transition states. My research actually involved trying to isolate intermediates. They're very difficult to observe because they will very quickly be turned into more stable reactants again, or go in the end to produce the ultimate products. And so they're very hard to isolate. They require special types of instrumentation experiments to see. And so that's what I did my research thesis on. And so the intermediates represented by these troughs here. When we look at a transition state, the geometry and basically the progress of the reaction can be estimated based on what's called the Hammond postulate, which states that if the transition state is closer in energy to the products, its appearance will be more like the products. So the bonds will be more broken, and the bonds will almost be formed, and it will almost look like the product. It will look more like the product than the reactant. Whereas if the transition state is closer in energy to the reactant, the transition state will appear more similar to the reactants, which is useful sometimes for determining what will happen in a reaction, understanding that Hammond postulate. As we move forward in next week, when we're going to talk about reactions, we want to evaluate what will react with what drives a reaction, so what makes a reaction spontaneous, and what drives most reactions is that a negative substance is or a substance with a negative portion on the molecule is attracted to a positive portion on another molecule. And so those molecules that have negative portions, or they have electron pairs, lone pairs that can be donated, are called nucleophiles. So nucleophiles include negative ions with lone pairs. They include neutral molecules with lone pairs, which are not quite as good nucleophiles because they're holding on to their lone pairs better. But they can behave as nucleophiles. Also, electrons involved in a pi bond are nucleophiles because, remember, pi bonds are weaker than sigma bonds, so those electrons can be more easily donated. So these are three classes of nucleophiles, either negative, neutral, or pi bond. That's as opposed to an electrophile. An electrophile is something that is positive, and it can accept electrons to make a bond. So these include partially positive atoms connected to more electronegative other atoms. They also include cations, which are positive. And so reactions occur because negative parts of one molecule are attracted to positive parts of another. And so the way we represent this is by drawing arrows to represent what is the nucleophile, where are the electrons coming from, what is the electrophile, where are the electrons going, or when bonds are breaking, where are the electrons going. So we have four different ways that electrons move. One is called the nucleophilic attack, one's called loss of leaving group, one's called proton transfer, and one is called rearrangement. And so proton transfer is an example of that. Is here it involves two arrows generally. You start your arrow on a lone pair. That lone pair is going to make a bond here with a hydrogen atom, and remember it leaves actually as a hydrogen ion, so both electrons in the bond that it used to have will be left behind on whatever it was attached to. That's a proton transfer. Loss of leaving group involves one arrow. It's simply the breaking of a bond, and those electrons that are in the bond are left as a lone pair here on the oxygen. This oxygen does have two lone pairs now. The minus H2O is saying that water left. Water was leaving the molecule. Another type is carbocation rearrangement. In a carbocation rearrangement, either a hydrogen or a methyl group essentially moves its bond. So this carbon, instead of being bonded to this carbon, these electrons will go here and produce a bond to this carbon instead, because this carbon has only 3 bonds and no lone pairs, so it can take a 4th bond. Finally, the last kind is nucleophilic attack, and this is where a nucleophile, some electrons on a negative or neutral or alkene compound, those electrons will go and attack a positive site on a molecule and create a bond. And those are the 4 types of arrow pushing that we're going to see over and over in mechanisms that you also saw in Chem 12. Also, what you may have noticed is that some of these arrows are written 2 ways and some are written 1 way. The question is, how will you know whether you should write a 2-way arrow or a 1-way arrow? And the way you determine that is based on the relative energetics and kinetics of these. And so here's some shortcuts to estimating that. If the attacking nucleophile is a good leaving group, it will be a reversible attack. So water here is a good leaving group because it leaves as a neutral molecule. In Chapter 7, we'll talk more about what makes a good leaving group and a bad leaving group, but generally a good leaving group leaves as a neutral molecule like this water. So if this were to leave, it can fairly easily leave by loss of leaving group to produce a neutral molecule water. That's fine. Now this is as opposed to, for example, if you have this, OH would be a terrible leaving group because if it leaves, it's going to leave as a negative ion, and that's not stable. It's going to want to go and attach itself back to the positive thing, but the water doesn't want to so much. That's why this is reversible. If a nucleophile is a poor leaving group, methyl is another example, hydroxyl, then that will not be a reversible reaction. So methyl is a terrible leaving group. It leaves as a negative ion. Carbon hates having negative on it even more than oxygen. We can evaluate that based on ARIO. Remember atom in ARIO. Oxygen is a better atom for keeping a negative charge than carbon and stabilizing that charge. Finally, proton transfer. If the pKa difference is 10 units or more, then we write a 1-way arrow. If it is less than that, then we can write a double. And that concludes Chapter 6, and that concludes our complete review of Chapter 1 through 6 in Chem 212. This was a bit of a long video, but I hope it was a thorough review for you. Next week, we will do Chapters 7 through 14, and I look forward to seeing you.